Good afternoon, everyone. This is Alex Canney with Preferred Utilities. Looking forward to beginning our second weekly webinar. Just a little bit of introduction for myself and for David Eoff. We were able to put this together, and we're going to be doing the live Q&A afterwards. My name is Alex Canney. I'm the Northern New England sales manager. Been with Preferred for coming up on about 10 years now, and really focusing in on mission critical fuel oil applications for hospitals, data centers, production facilities, and things like that. Joining me is David Eoff, our national sales manager, and he's a mechanical engineer that has spent most of his or all of his career in the boiler industry, and he's been with Preferred for about 14 years now. Really looking forward to answering your questions in the chat channel and the live Q&A afterwards. So if you get a chance, click on the chat button there and just type in a quick question for us, and we'll talk to you soon. Thank you very much.
All right, good afternoon. Thank you for joining us. We're doing a short webinar today that is designed to show you guys how to use the fuel system design web apps that we put on the Preferred website. I'm David Eoff, and I have Alex Canney with me. We are both experienced engineers at designing fuel handling, storage, and supply systems for emergency generators and also boilers. So first, real quickly, going to go over the agenda. We're going to show you a couple of slides that give you an idea of the types of fuel systems we're talking about. Alex is going to show you our fuel load calculator that'll help you figure out how much bulk storage you need. Then we're going to go over our pump and pipe sizing web app. And then finally, we're going to show you an app on our website that'll help you write an entire facility fuel oil system specification. And then we're going to leave time to entertain questions at the end. So this is what we're talking about. It's a system that supplies one or more emergency generators, topping off either day tanks or belly tanks, using a transfer pump set that's pulling from either underground storage tanks or above ground storage tanks. So many jurisdictions have rules about how much fuel you have to have on hand. In Texas, hospitals are required to have 24 hours worth of fuel on the facility. Florida just passed a law a couple of years ago saying that you have to have enough generator capacity to air condition your living space, and you need to have 120 hours of fuel on the property. This is applicable to nursing homes and assisted living facilities. And there's just a couple of, the math in this program is easy math, but there's a couple of considerations that you need to bear in mind. And really that's the value of the program, is that it automatically prompts you for these things. So if a jurisdiction says you have to have 120 hours worth of fuel, that has to be usable fuel. Not all of the fuel in a main tank is usable. You have two things, ullage and drop tube gap. They're both about 10% of your fuel that's not available. Ullage is the amount of empty space at the top of the tank. So typically you can't fill a main tank above either 90% or 95%, depending on your jurisdiction. So a 10,000 gallon tank can only be filled to 9,000 gallons or 9,500 gallons, depending on where you are. Also, the drop tube for the supply pumps doesn't go all the way to the bottom of the tank. So you can lose up to 5%, 5 to 10% of your volume at the drop tube. Also, NFPA 110 requires that you carry 133% of the fuel for your designated runtime. So they sort of require a 33% safety factor. And then finally, when you have day tanks, the amount of fuel in your day tanks can be, it's usable fuel. So that can be added to the amount of fuel in your main storage tanks.
Here we have our Preferred website, and we're going to take a look at how to access our fuel load calculator. All of the tools are down here, and we're going to be taking a look at all of these three right here. We're going to start with the fuel load calculator, as David said. We pull this up. It's a fairly straightforward tool. As with the other ones, we have over here a place for you to fill in your name, company, email, and phone. That's so you can save your projects and keep track of them later. So starting with our runtime, we're going to put in some example numbers here. For some of the applications we're seeing in the Northeast, a lot of times we'll start with 72 hours of runtime. And assuming that this is a larger plant, we'll go ahead and put in two 1.5 megawatt generators. And this is in kilowatts, so you will need to adjust for that. And we can add more generators as well. As we go beyond 3, we can click this to add a space for additional generators if necessary. I will say if you're working on a project with more than 2 or 3 generators, definitely give us a call to go over that application. As we upsize plants, and especially the number of day tanks and number of generators, there is a lot of complexity that gets added. So here we have already our total consumption in GPH. Keeping in mind that this is going to be very applicable for most of the country. If we have an application in New York City or California, and we'll talk about this again later as well, we may have conditions where these general consumption numbers might not be applicable. For instance, if we have a return from our generators going back to our main tanks rather than the local day tank or belly tank. Here we have a place to enter in our percentages for ullage or ulage, depending on how you like to pronounce that. And in this case, we will use the 10% figures that we went over previously and add another 5% for generator testing. So for this, we can go ahead and just call this example. And put in all of our information. That way we can go ahead and save our work. And so we have all of these numbers here. Very straightforward tool, but it gives us a nice way to calculate the total amount of fuel needed in the system. As David mentioned before, that doesn't necessarily mean that we're going to run out and buy a tank that's exactly this number of gallons, but it does give us a good idea of where to start to now choose a nominal size.
So in Alex's example, the web app calculated 18,900 gallons of fuel needed. So that would obviously get rounded up to 20,000 gallons, and either one 20,000 gallon tank or two 10,000 gallon tanks, depending on what you have the real estate for and what sort of redundancy you want to build into the system. So next we're going to talk about the preferred pump and pipe sizing web app. And for that, we're going to provide a little bit of orientation. This is a typical layout that you're going to see for generator fueling. This one shows 2 day tanks filled by an automatic transfer pump set that can draw from one of 2 underground storage tanks, those USTs. For above ground storage tanks, we use the acronym AST. But what the pump and pipe sizing program is intended to do is make sure that your suction and discharge conditions for the transfer pumps are within the limits of what the pumps can supply.
Here we are at the preferred website. The next tool that we're going to be taking a look at is the pipe and pump sizing. Go ahead and click on that. The way it is laid out, header at the top here showing us our pump suction value, discharge value, and then we have section 1 piping layout and sections 2 through 4 that we're going to get to in a little bit. Off to the side here, once we input a minimum number of values needed to calculate the system, we're going to see these numbers update off to the right as well. The first example that we're going to look at is the most simple and straightforward. That's the tank below the pump, where an anti-siphon valve is not necessary and we don't have any up and over piping on the suction side. We go ahead and select that, and it's going to update this here. We get a nice little check mark for this section, and then we hit next to move on to the parameters. So you'll notice that as we move along, we still have 0 values here and off to the side, and any of the sections that are highlighted in red are going to need to be filled out. Now, if it's a section that you're not using and it's a 0 value, just go ahead and put a 0 in there to let the program know. So in this case, I'm going to do an 8-foot tall tank For our B value, the vertical distance between the top of the tank and the center line of the pump, I'll go ahead and use a value of 3 feet. Pump discharge to user elevation in feet. This is going to give us our total head due to gravity. And let's say for this one, it's about 50 feet. Now,
So that's about a 4 or 5 story building.
that's correct. And if we need to go up to a very, very tall building, that's certainly doable. David, what would be one of the taller applications that you've seen recently throughout the country?
We have done some 20-story buildings in New York City and San Francisco.
And those are no problem?
We've got 2 types of pump sets, 50 psi discharge and 100 psi discharge that are in our catalog, but we can also use rotary screw pumps that can go up to about 300 psi for the real high-rise applications. They're just kind of a custom pump for that application.
Nice. And the last one that we have here is pressure required at the user in PSIG. Now we can put 3 psi in here as really a safety factor, just to be conservative. But for most day tank applications, the fuel is going to be at 0 psi as it enters the day tank because it's a vented tank. For some older applications, such as a high pressure supply loop for a boiler plant, that would be much more of a factor where we're looking at something like 70, maybe 100 psi. But for most of these applications, once it gets to the generator, it's going to be at atmospheric pressure. We have our number 2 fuel oil selected, which obviously the properties are going to be very close to diesel as well, practically interchangeable for the calculations that we're performing. We have our transfer pump set. In this case, we're selecting a LO103 size, and we're going to put in a value for altitude here. This is going to be significant on the suction side of the system, as David will talk about in a little bit, because this will dictate how much net positive suction head is available based on that ambient air pressure. So in this case, we're going to put in 100 feet above sea level. And we have a nice little box here that gives us some reference values such as viscosity, flow rate, atmospheric pressure, etc. So we can go ahead and hit next for suction piping. Now, if at any point when you're working through this, you want to go back and revise something or edit something you've done, you can just go ahead and click on the section itself, and it'll take you back to whatever section you need to. So moving forward to the suction piping, this is the most critical part of the system as far as trying to get the valve counts, total length of pipe correct. We want to make sure we're as precise as possible because we have a very limited amount of pressure to work with on the suction side. So here's where we put in our total length in feet for the suction values. And if you have a valve that is custom, maybe something that's not offered here, or you just need more valves than we're allowing in the drop-down menus, you can use an equivalent length of pipe in this length value right here as well. But we're going to take a look at a system that has about 50 feet of length, and we're going to be selecting 1-inch pipe for the suction side. For 90-degree elbows, I'm going to go ahead and put in 6. And for the foot valves, of course, the foot valve is the item that goes at the bottom of the drop tube in the main tank, so we would only select one of either single poppet or double poppet foot valve. And we're going to select a lever gate valve as well. And here for the strainer, I'm going to select a duplex strainer, size 1 inch. And for most generator applications, it's going to be a 100 mesh basket. Now you'll notice off to the right here we have an option for secondary piping. This is a great option because we may have a condition where we have underground piping coming from a remote main tank, a remote bulk storage tank that's at one size, and then we have a secondary set of piping when it comes above ground that's at another size. And since the suction side is so critical to get these values as close as we can, we allow you to break those up into 2 different sections and then add those values together. All right, moving on to the discharge piping. In this case, we're going to select 1-inch discharge and total feet. Let's go ahead and put in 150 feet. Now you notice this was the last field that was highlighted red. So now that that's filled in, the header at the top is going to give us our pump suction values, keeping in mind that those are in inches of mercury. and our discharge values, which are in PSI, which matches what you would see on a compound gauge in the field. Our values off to the right here are populated as well. And the nice thing about this section right here is that not only does it give you the total values like it does at the top of the screen, but it also shows you which values are contributing the most. So if we're looking for a little more headspace on an application where we need to get a little more vertical space out of it, or we're trying to see what's the smallest we can go on piping, we can see if the most important contributors are our friction loss due to the velocity of the fuel and the size of the line and the valves, or if it's the geometry of the piping itself, how far vertically things are from each other. So all of those values are off here to the right. And then we have the option at the end to go ahead and save our project. We put in the email here. And David, as far as when they're putting in email addresses for these different tools, how are those used on our end?
So what's going to happen is when you give us your email address and a project name or your name, it's going to send me an email, and I check these every couple of days, and there's a place on our website where these leads are kept. And if you're in New York City, I'm going to forward your email to our New York City specialist. If you're in California, I'm going to forward you to our specialist there. In most other places, I'm just going to send you a quick email that says, I see you saved a project on our pump and pipe sizing program. Did you have any questions I might be able to help you with? And if you weren't sure about something, feel free to just reply to that email and ask whatever question you like, and we'll start a dialogue. I've been doing systems like this for about 14 years, and I not only do I design them, I occasionally start them up. So I've seen quite a bit of everything, and I can guide you in specifying a system that's going to work for your application.
And that's really our goal here. We're not going to automatically put anybody on a spam list or anything like that, correct?
No, you'll get one email from me, and if you don't reply to it, you'll probably never get another email from us.
Excellent.
You showed us a system that works. The pump suction is only 9 inches. That's within the 15 to 20 inches that the pump allows. And discharge pressure is 22 pounds. So that's less than the 50 PSI maximum discharge pressure. Now let's go into that system and do something wrong. So let's say we change the strainer from 1 inch to ½ inch. Show us what that looks like.
So if we go to the suction piping, let's say we choose a strainer that's, well, the smallest they'll allow us to choose is 3/4 inch. You'll notice when that updates, it really doesn't make a huge impact on the system. But if we were to, say, go into the parameters here, and this B value, let's say we tried to design a system where there's 20 feet of vertical between the center line of the pump and the top of the tank. Keeping in mind that not only is that a large vertical here, but also we're designing for worst case scenario, so the tank may not be full. So the tank size will be added on top of that for our priming value. And you'll notice immediately we get a red number here up at the top for our pump suction value. It's above 20 inches of mercury. And then if we go over to our values here on the right, not only do we get a red indication for the priming static lift, but we get to look at all our values and see, okay, if I need to dial back on something, what's going to be the most effective? Well, our biggest impact here is static lift. Our second biggest impact is our friction losses, but those only amount to about 1.5 inches of mercury. So if we're going to bring this system back into a line, it's going to be on the static lift side. So if we were to bring that value down to something more reasonable, you can see the system, the numbers here go back to green and it's happy again. And the values that we're going to be typically looking for, I like to design, at the design phase, I like to keep it around 15 inches of mercury. We can do up to 18, 20 in some cases in the field, but there are things that change between the design phase and in the field, and typically it's not going to make it easier on the system. So I like to leave a little bit of cushion. Once we get up above 20 inches of mercury, that's where we're going to be likely for cavitation, and we're going to see a degradation of pump performance and lifespan as well.
So that was an underground storage tank. So tank below pump. Show us, if you could, what an above ground storage tank application might look like.
So depending on the configuration, we're usually, for an above ground situation, we're going to have tank partially above pump, something along these lines. So when we go into the parameter section now, you can see that some of these dimensions have changed how it's laid out. And in this case, we have an anti-siphon valve because if the fuel line is broken anywhere below the surface of the fuel in the main tank, there is a potential for siphoning that fuel out onto the ground. So now, in this case, we have an additional value here. So if we were to say an 8-foot diameter tank, this value E right here is actually very important as well, because even though we have a tank and a pump that are about on the same level, if this E value gets very, very large, the problem won't be necessarily under operation. The problem could be under commissioning and startup, because if this line is empty, the pump is now going to have to pull fuel up that length, that value of E, all the way to the top before it can now come down the other side and into the pumps. So you may have a situation where if that value is very large, if everything's perfectly primed, it's going to run fine. But on startup and commissioning, if there's not a way to manually prime that, it may not actually be able to pull that fuel up and over in a dry system. Keeping in mind that positive displacement pump set like this, if the pumps are bone dry, they're not going to be pulling air quite as efficiently as they would pull fuel with those internals wetted by the fuel itself.
So one thing to bear in mind, if you make that E value especially large, we call that an up and over in the piping, and up and overs should be avoided at all costs. It takes suction to get the oil up to the top of that up and over, and then you recover that pressure again on the other side, so the pump doesn't see all that negative pressure because it gets credit for the weight of the oil in the right side of that up and over, if you will. But bear in
Correct.
mind, you can have very high suction at the top of that up and over, and the suction can be so great that you actually vaporize the number 2 fuel and cause it to bubble up there.
That's right. In extreme cases, we can have real issues on that run of piping. And in fact, one of the other problems, if that's not fully purged and manually primed on startup, the horizontal run of that up and over can be partially filled with air because it's very hard to bring all of that air out of that section of pipe down and through the pumps. So that can actually increase our fuel velocity in that section of piping, increase our friction, and throw off our numbers. And you'll see off to the right, in this case right here, even though our pump suction value running under steady state is really not that bad, our static lift is actually going to be quote unquote positive in this case. Our priming static lift is very, very bad. So if this system was to be manually primed, it could run well, but if it was just turned on in a dry condition when installed, there's going to be issues.
So I always try and call out a priming T at the top of that up and over, and the priming T is just a T with a ball valve and a plug. And when you prime the system, the contractor will take the plug out of the valve, open the valve, and then most of the fuel oil contractors will carry a little 1-gallon can with a little squirt nozzle on it, and he can use that to fill up that piping in the up and over. And when that piping is completely full, you turn on the pumps and they move oil right away.
Yeah, it's really the best way to go for the system. Even though positive displacement pumps are described as self-priming, self-priming is kind of like walking distance. How much time do you have and how much wear do you want to put on these pumps when they're dry? They're going to wear at a much faster rate than if they were flooded with fuel and running happy. And in a pinch, I would also say that if you have a system in the field where you have an anti-siphon valve but you don't have a priming funnel, you can also make do by putting fuel into the anti-siphon valve, which should be installed at the highest point of the system.
That's a great tip. Okay, so Alex showed us how you can use the pump and pipe sizing program to make sure that the suction piping and the arrangement of your tanks versus your pumps and the arrangement of your day tanks versus your pumps is going to work within the limitations of the pumps. And with positive displacement pumps, we're mostly concerned with the suction side because we're limited to about 15 to 20 inches of mercury. And the way I like to think of the suction side of a pump set is that you can't really pull a liquid. All you can really do is push a liquid. So the pumps evacuate the pipe, and then it's atmospheric pressure that forcing on the main tanks pushing on the pipe that pushes the oil along the pipe. And the reason that there's an elevation field in the pump and pipe sizing program is when you get up to higher elevations, there's less atmospheric pressure there to push the oil through the suction side of the system. So I'm always careful, especially if I'm doing a job that's high altitude, to make sure that I include that elevation number, because there's just less ambient air pressure there to push on the suction side of our pipe system. Now, the discharge side is totally different. There, the pumps are pushing the oil, and we have plenty of pressure there because the preferred standard pumps are either 50 psi discharge or 100 psi discharge, which is actually quite a lot. And if we're doing a high-rise building, we can go to rotary screw pumps that can give us up to 300 psi of pressure. So there's just a lot more pressure available to us on the discharge side of the system than the suction side. And that's why we take such a hard look at the suction side. So what I'm going to show you now is that you can use that pump and pipe sizing program also to make sure that your return piping is going to work with the system. Whenever you have an above ground storage tank, you're going to see a return pump on each of your day tanks, because you need to be able to evacuate that day tank if you start to overfill it. If you have underground storage tanks, like we show here, in fact, you can use gravity return or just an overfill line. Even when you have an underground storage tank, we still recommend a return pump, because that allows you to take fuel out of the day tanks during commissioning to make sure that the pump controls and all the float switches in the day tank are working. And also it allows you to test the system or exercise the system. You can put it into your maintenance protocols to periodically go and test the fueling system. So the return pump will have a handoff auto switch attached to it. Energize that return pump, let it pull the oil level down to the pump on switch, and make sure that the supply pumps come on automatically and top off the day tank like they should. So even when you have underground storage tanks and gravity return will work, we still recommend return pumps.
So I just would like to add on the return pumps. Sometimes we'll get some hesitancy by design engineers to add a return pump to a system if it's a mission critical application, and they see that as a possible point of failure for fuel to be removed from the tank. Some of the ways we can handle that, we can put a drop tube on that return pump that only goes down to about 40% of the tank. So around 40 or 50% is typically where we would have our low alarm point. And that'll allow us to fully test the level sensor in that storage tank, but not allow the return pump to pull it down unnecessarily low or starve the tank if there was some sort of controls malfunction.
To run through using this program to check return piping, I'm going to pick tank below pump, because typically the return pumps are mounted right on top of the day tank. And that's all for that. So I go on to next parameters. Now, if you know the height of your day tank, you can put it in here. I think the tallest day tank preferred makes is 4 feet. So I'm just going to put in 4 feet. And the pump is usually mounted right on top of the tank. So to be conservative, I'm going to put in a foot. And then if our main tanks are underground storage tanks, it's very likely that this pump is located above the underground storage tank. So being conservative again, I'm going to put in 0. And then I'll put 5 psi here just so that we have some pressure left at the end of the loop. The rule of thumb for return piping is that it should be 1 line size larger than your supply piping. And your return pump needs to be able to flow more oil than your transfer pumps. And there's a couple of exceptions to that rule that we'll cover here in a little bit. But let's just say the example that Alex used, I think he picked an LO103. So that's 86 gallons per hour. I'm going to go to the next size return pump of LO104 that's 155 gallons per hour. Because in a worst case scenario, let's say the plant operators put both the supply pump and the return pump in the hand position. We want the return pump to be able to outrun the supply pump so that we don't get an overfill. An overfill is about the worst thing that can happen in any kind of a filling situation. So I'm going to put in some altitude, not that much, just for fun. So we picked an LO104 at 155 gallons per hour. When you have multiple day tanks being supplied by one set of transfer pumps, what we'll often do is we'll put a flow limiter in the piping to each of those day tanks, and we'll limit the amount of flow to the flow that we want for that individual day tank. That way, the return pump can be sized just to be larger or more flow than the flow limiter. It doesn't have to be more flow than the transfer pumps that are sized to top off all the day tanks. And that's important because it can really reduce the size of your return pump down to something more reasonable.
Also, for your day tank controls, if we have a large plant with multiple day tanks and multiple generators and it's seeing the full flow of that transfer pump set, there are cases where on smaller day tanks, depending on where you're located, it can overwhelm the level controls. So we'll want to limit flow for that case as well.
So I'm looking at my chart from Catalog 25, and we've got it here in the spreadsheet. This is from Preferred's Catalog 25, and it's also on our website. It gives you all the useful flow information for all of our standard size pumps. And the 104 that flows 150 gallons per hour has half-inch outlet and 1-inch inlet. And for a first guess, I'll usually go one pipe size larger than the inlet or the outlet. So in this case, I'm going to go 3/4 inch pipe on our suction side. And because the return pump is sitting right on top of the day tank, the length of pipe is only going to be the height of the day tank. So in this case, let's be conservative. We'll call it 5 feet. It's really not going to matter. There might be one elbow and there will be a foot valve in there. And there typically won't be a strainer. So I'm going to go on to our discharge piping. And now the discharge piping is going to be real. 3/4 inch is one line size larger than the outlet of the pump. So that's what I use as a starting point. My total length of pipe, let's call it 250 feet. Should be able to take this from a drawing. Since I don't know how the contractor is going to run the pipe at this point, I always pick the most elbows it'll allow me to do, and that's 10 elbows. And we actually have, the next time we revise this program, it's going to let you do more than 10 elbows. I'll pick a 45. You're not allowed to have any valves in your return line, so there's not going to be a lot here. If there are multiple return pumps all feeding the same return header, there'll typically be a check valve, so I'll include the check valve. There's no strainer. And now you can see that we started to get some information up here. So our discharge pressure under these conditions is just 8.5 pounds. And our pump suction is 4. Everything's green, so that's okay. Now, one thing I would do differently is here in parameters, if I had an above ground storage tank, I would, I'd change this C number because then this pump is going to be below the top of the tank where we're returning fuel to. So if it's a 10-foot tank and this pump is already up 4 feet, we might put 6 foot in for C. I'm going to put 7 feet in just to be a little bit conservative. And our discharge pressure now is only 11 pounds. You can use the ATPS line of pumps, or really they're the LO series of pumps that we showed here. Or what you can do sometimes, especially if it's an underground tank and you don't need a lot of pressure, is you can use the pumps that are in our filtration sets. They are high flow, low head. So you can go up to 1,200 gallons per hour at 25 psi discharge pressure, and these are higher flows. So, for instance, that PF 505 pump at 1,200 gallons per hour will outrun the largest ATPS supply pump. That's a 206 at 1,100 gallons per hour, and it'll be a smaller motor. In this case, it's only 3/4 horsepower because it's less pressure. And a big advantage is that all of these filtration pumps are 120 volt single phase, which means you're already going to be bringing 120 volt single phase power to the day tank anyway for the controls. This means you don't have to bring any additional power. You don't have to bring a 3-phase source into the day tank as well. So it cuts down on the electrical interface to the day tank.
And David, if I could, just for some of the folks here in the Northeast, the calculations that you're describing here doing the double check for the return pump. This is typically going to be for a system where everything is basically at the same elevation for the most part. We're not talking a high rise, but is spread out quite a bit. So an application like you would see in Texas.
The systems we have in Texas tend to be single level. So our pumps, our generators, and our tanks are all going to be at the same level, usually. Sometimes we'll have buried tanks. So the projects that I see in Texas are pretty spread out horizontally, whereas in the Northeast and on the West Coast, we see projects that are spread out more vertically, where the main tank might be in the basement, the pumps might be in the basement, or they might be on the first floor, and then sometimes we're filling day tanks that are on the roof of the building. So that's why when we go to this next program, it's going to say, if your project's in New York City, call our New York City specialist, and if your project's in California, call our California specialist, because not only are the applications different, but the rules are different in those two states as well. So okay, so we just showed you how you can use the pump and pipe sizing program and sort of force it to verify that your return line sizes and your return pump calculations are going to work. There's another system that you can do with our pump and pipe sizing program if you massage it a little bit, and that's systems with submersible pumps. So I just want to go on record that Preferred Utilities hates submersible pumps. We supply positive displacement pumps. So, the number one reason why we hate submersible pumps is we don't make them. The number two reason is they're less reliable. If you need to work on them, they're in a sump that might be full of water, and you cannot believe the curves that they put out for submersible pumps. We had a project recently where someone made us use submersible pumps, and the submersible pumps were pumping out of a main storage tank up to day tanks on the second floor, and the pumps would not move any oil into the day tanks. And our technicians have been over the system head to toe. There was nothing wrong with it. We brought out a technician from the manufacturer of the pumps, and he looked it all over. We showed him the pump curve that said that we should be able to get the fuel up to that height, and he shrugged his shoulders and so you can't trust the pump curves. So you got to take them with a little bit of grain of salt and not push them to their limit, because they can be a little optimistic. That being said, there are a couple of situations where you have to use submersible pumps. If you have underground storage tanks that are deeply buried, a positive displacement pumps may not be able to pull the oil out of deeply buried, large 12-foot diameter tanks. Also, you may have underground tanks out in a parking lot a long ways from a building, and the engineer or the architect won't let you put positive displacement pumps near the tank. They don't want the eyesore of a pump set enclosure over their tanks. So if the only place they'll let you put the positive displacement pumps is 300 feet away from the main tanks, it's unlikely you're going to be able to pull oil 300 feet reliably. So that's a situation where submersible pumps might work better, so you can push the oil through the whole system. So you would start with this pump curve, and I don't remember if this is Red Jacket or FE Petrol. Someone else might recognize the part numbers. But if you need, let's say, 3,000 gallons per hour, that's 50 gallons per minute. We'll go up here. This is the 50 gallon per minute line. And I know it's a little small, so you'll have to trust me a little bit. And are using either the 150U1 or the X3P 150U1, we get about 75 feet of head at 50 gallons per minute. And it's important to check, and this curve is done at a specific gravity of 0.78, so this is an oil curve. And if we take that 75 feet of head and multiply by 0.423, we get about 34 psi of allowable pressure. So I'm writing that down, 34 psi and 3,000 gallons per hour. Now we can go back into our pump and pipe sizing program and start at the top with piping layout. And in this case, The suction side is really not going to matter. So I'm just going to pick one. And we're going to do tank below pump. And then go to parameters. And here you get your choice of fuels. You don't have to do number 2. You can do number 4 or number 6. And these are all of the pumps that Preferred has in their ATPSF duplex pump sets. Or you can go down here to custom application. And with custom application, you get to put in whatever flow you want. So we decided this system's going to flow 3,000 gallons per hour. And I'm going to move on to suction piping. The calculations for the suction piping and the discharge pressure are completely separate, and they're not really related in this program. So I'm just going to oversize everything, and it really doesn't matter because with submersible pumps, there is no suction piping. So I skipped parameters. So now our submersible pump is sitting here at the bottom of this tank. So the A dimension, we're going to make 0. The B dimension, we're going to make 0. And our C dimension goes all the way up to the day tanks or whatever it is we're filling and goes down to the level of the pump that sits in the tank. So if we're filling day tanks that are on the 2nd floor, that's a 4-foot tall day tank, call it 10 feet to get to the 2nd floor. If this is a 10-foot tank, the pump's going to sit near the bottom, so we'll call that 10, and our C dimension is going to be 22 feet. And let's say we need 5 psi at the day tank. So what we need to remember about this application is it's all discharge pressure, and all of our piping and all of our vertical lift really is downstream of the pump. So it's all incorporated into this one C value here. So we already did suction piping. We are going to move on to discharge piping. And for 3,000 gallons per hour, I'm just going to guess 3-inch, and we'll see how that goes. Instant feedback, we're at 14.7, so far we're good. This is still left over from our old example, so I've got 10 elbows, which I like to keep, a 45. Let's add a Schematic valve in there. Or no, let's not do it. Let's do a lever gate valve. That's more common. And we'll do a globe valve, and we'll do a couple of ball valves. And as you can see, the pressure didn't go up very much. So our pump suction doesn't really mean anything, but our discharge here is 15 psi, and we were allowed from the pump curve 34 psi. So at 3-inch discharge piping, this is really comfortable. So I'm going to go down to 2.5-inch discharge piping and see where we're at. 17.7, which is still good. So I'm going to go to 2-inch. And we're at 23. And by the way, you can input the total number of feet of your piping. I think 250 feet was left over from our last example, but it works for this example too. Just for fun, let's see what 1.5 goes to. So 1.5 is 44. So now we know. 2-inch piping gives us 23 psi. The pump will do 34 psi. So even taking that pump curve with a grain of salt, this looks like a very conservative sizing on the line at 2-inch. And with just a click of the button, you can check the next size lower. So if somebody asks you, couldn't we run this 1.5 inches? No, you can't. At 44 psi, it's way over what the pump will deliver. So now we know that 2-inch is our pump size. And you go down to the bottom, and you can you put in your information again, save your work. It's saved. And then you can go back and you can access this at any time again from our website. And just like all the other examples, it keeps track of a running calculation here all the time. And if one of these values gets out of what we put in as preset ranges, it'll flash red and let you know.
David, if somebody had a custom valve that they had an equivalent length of pipe value for, could they just add that into the total discharge pipe or suction side pipe.
Yeah, and that's really an easier way of doing it than trying to force another valve into the system.
Right.
If you know the CV of the valve, uh, you can go into this chart here and pick a similar valve that's going to have a similar CV, or if you've already worked out the equivalent pipe length method, just add it here. So if
Correct.
it's in the
Yep.
discharge line, then 250 might turn into 300. And I like to do a little bit of sensitivity analysis here because I've measured, I think the pipe is going to be 250 feet. What happens if the contractor runs it a little differently than what I laid out? It's 300 feet. Yeah, we're still good, 24.37. So because our piping friction losses are not terrible, increasing the length of the pipe a little bit doesn't blow up this discharge PSI number. And in general, if you stick with our guideline of we don't like to move diesel fuel more than 7 feet per second in a pipe, and as long as you don't exceed that, your piping losses are going to be pretty reasonable. And most of this discharge pressure that you see will be static lift, not frictional losses.
So here we are in the preferred fuel oil system specification configurator. As David mentioned before, it's very important if you're located in New York City or California that you reach out to us for a custom specification. But for the rest of the country, and especially for where I'm located in the Northeast, this is going to be a great start to a specification. It's going to give you most of what you need, and it's pretty straightforward to set it up. So you choose how many generators are in your system. I'm going to go ahead and stick with 2 as we've done in the previous examples. And it's going to ask if day tanks are required for the generators. Now, if you were with us last week, we talked a little bit about the day tanks versus belly tanks trade-offs. And just briefly, I'm going to say today that we recommend, if at all possible, if you have the space, to go with the standalone day tank. And it's going to ask you if you want return pumps on your day tanks. Now, the return pumps are a great item. We can use them to test, recirculate fuel, and everything. So if at all possible, especially if this is a mission critical application where we're talking hospital, data center, that sort of thing, we're going to want to select yes for this. Now you also have an option for how many main storage tanks are in your system. Most systems are going to be 1, but we can accommodate more as well and have some verbiage in there for how we're going to dispatch fuel from tank.
Alex, there's 2 reasons why we asked this question. One is that the specification that this tool is going to create is an entire facility fuel oil specification. It's the whole section. The verbiage for the preferred stuff is specific to preferred, but for the things like the main storage tank and the containment piping, it's going to be somewhat generic. The other reason we ask about main storage tanks and the capacity of the storage tanks is it's used for sizing the filtration system or the fuel polisher down below.
That's a great point. And I would say, even though the sections on, say, piping and bulk storage tanks aren't based on equipment that we necessarily provide in every case, we do work a lot with industry partners, and so we have expertise on those sections of the system that we can provide as well if you have any questions. So we'll take a look at the total capacity. In this case, let's say it is 2,500 gallons. Is the main fuel oil storage above ground? In this case, we're going to select yes. Now, if you have a situation where the tank is vaulted, so the tank may be below grade, but it's inside a basement, we're going to go ahead and select an above ground tank because the construction and specification are going to be nearly identical. We can also take a look at a fire rated tank, a UL 2085. This may be required by code or insurance, depending on the amount of fuel being stored and what the requirements are for the space. We're going to go ahead and select no, so it's going to be more of a typical UL 142 double wall bulk storage tank. I'm going to include double wall containment pipe. And if we have a situation where piping is running outside, and we may want to take a look at some things like heat trace, containment pipe leak detection, all of those things are going to be involved as well. At this stage, we're just going to select yes, and we're going to indicate what motor voltage is available to the system. And then we get down towards the end here, and it's going to ask if we want to specify an automatic fuel filtration system. In subsequent webinars, we're going to be taking a closer look at all of the factors that impact fuel oil quality, but the general trend in the industry, especially with larger amounts of stored fuel, lower consumption, where a lot of facilities may have been sharing consumption with a boiler plant, and now boiler plants are going to alternative fuels, to natural gas, and so the only fuel being used up in the system is being used up by generator periodic testing, and things like ultra low sulfur diesel. All of these factors are contributing to some systems that existed that were a bit marginal, but now we're having fuel quality issues. And certainly for new systems, if we're talking a mission critical application, there are a lot of reasons why we're going to want to specify an automatic fuel filtration system that's dedicated to maintaining the quality of that fuel. So I'm going to go ahead and select yes. Now, we were looking at previously a 103 sized automatic transfer pump, and you'll see there's nice little links right here that'll take us back to our fuel load or pipe and pump sizing calculators, should we need to double check any of those things before we move forward with the specification. We can go ahead and give it a name, company, email address, phone, and either save or save and create specification. So it tells us that it is saved, and it brings us to this page right here. So as you can see, we're outputting this in a text format. Now we can go ahead, Control A, select all, Control C, copy, and then we'll pull up a brand new word processing document with a blank. And then what we can do, we select a blank document, go ahead and paste that in, Control V, and that's going to give us a clean copy of our specification. Now, in some cases, you may want somebody local, even if it's not New York City or California where the regulations are going to be very different, you may want somebody local to go ahead and take a look at this. Any of our sales engineers would be happy to take a look at the spec that's outputted, check it for completeness, but also to go in and customize certain sections based on the application.
Alex, the specification creator gets the very basic systems about 100% right. If you're doing something that's a little odd, you're going to need to go into this Word document and either add or delete things for your own requirement. But for me, this is a real time saver because it takes about 90% of the effort out of doing a specification.
That's right, and most of the things are already going to be included. Most of the customization work may be removing some redundant sections, so there's not a lot that you have to really add in at this point.
Okay, so those are our three main web tools for helping you design and specify a fuel handling system. If you want to know more about preferred utilities, you can check out our website at preferred-mfg.com, or you can go to David Bond's LinkedIn page. David Bond's the owner of Preferred, and he updates content on this page every Tuesday, Thursday, and any night that he can't sleep. So you might see stuff show up here at 3 a.m. on a Sunday morning. But there's lots of posts here about stuff shipping from our plant, interesting projects. There's a bunch of white papers there. He encourages our engineers to write research papers on interesting topics. So if you have any interest in the boiler industry or fuel handling systems, you'll find a lot of cool information here. All right, so that's it for our presentation. We're going to go live now, and Alex and I will take your questions. Thank you, everybody, for tuning in. One thing I wanted to point out before we get going is that the calculations behind the pump and pipe sizing program come from that Crane Flow of Fluids book. Mine is orange. I'm not going to tell you how old it is. It's very old. But that pump and pipe sizing program was an Excel spreadsheet for about 10 or 15 years. And then about 3 or 4 years ago, our chief engineer went over the calculations again, and then we put them into that web app. So now it's available online to everybody. If you guys have questions about what you just saw, go ahead and email us at at one of the email addresses above, and I'm going to check my email and see if we have any questions here. Bear with me
We
just a
had a few
second.
questions in the chat channel as well. I don't know if you would like to start with those.
Sure. Why don't you start us out?
Okay. Jean Fontaine asked, how do you design a fuel oil system to be above a hurricane flood zone like New York City? And I was able to give a quick answer to Jean in the chat channel, but I thought it would be nice if we gave her a longer answer and for everyone else's benefit, David.
Okay, so um, we made some changes to how we did fuel handling systems after Hurricane Sandy, but really what preceded that was Hurricane Katrina. And in Hurricane Katrina, most of the New Orleans area was flooded. About anywhere I saw places where the high water line was 5 to 6 feet high. And I went into New Orleans about a month after Katrina, and you could just see the high water mark in all the places that were flooded, especially on like cinder block walls. And what we found was anything at ground level was inundated. So new construction after Katrina, we ended up raising the generators and the day tanks and all the controls above the Katrina high water line. And that's the safest way to do it, is just get everything above the high water line. Um, there were underground tanks that were below the water line that were tight. Their vents were above the water line, and then I heard of stories where underground storage tanks got inundated by the water in Katrina um, through the vents or through the fill pipes that weren't above the high water mark. So that was the answer for the New Orleans area, was just move everything up. And then when Hurricane Sandy came through, we actually got a call from the fire marshal's office in New York City, asking if we had any experience with submersible pumps. And we said yes. And where are you going with this? They said, well, in New York City, a lot of our main tanks, our bulk storage tanks, are in the basements, and they can't be moved up. There's no real estate to move them up. So do you have any experience with putting submersible pumps in the main tanks, pumping up to positive displacement pumps that have the head to get the oil, up to the generators, whether they're on the second floor, the fourth floor, up on the roof? And we have done projects like that before. But what we ended up doing after Hurricane Sandy was we put our LO series of pumps, and we put them in waterproof enclosures. And now there are WP series of pumps, and all of our LO series pumps are available in waterproof enclosures. And we can get you some more information, or you can just Google preferred waterproof pumps and you'll see them. The
And also,
pumps in.
if you're in the chat channel, there's a link I placed in there that'll take you directly to that on our website.
Oh, that's cool. Thanks for doing that. So those are the two approaches we took. In New Orleans, we moved everything up above the flood level. In New York, where we couldn't, we made the part of the system that had to stay below the potential flood line. We made all of that waterproof so it could take the flooding.
Usually the first two questions I get when we talk about our waterproof pump sets are, what depth have we rated them to, and how do they run when they're not submerged? And I've been personally involved in testing that was designed to simulate, I want to say, up to 100 feet submerged depth, maybe 80 feet, quite deep. And we did some extensive testing as well, David, if I'm not mistaken, on running these quote unquote dry, because they are fully enclosed in a pretty heavy steel case. So there were concerns initially whether, is there longevity, overheating, things like this. And they performed well, just running, without being submerged also.
Yeah, I did a lot of the initial design on the waterproof pumps, and when I got it about 90% done, I realized that we had a TEFC motor, with a fan on the back of the motor to cool the motor, and now we've completely enclosed that whole design. So I thought we might have to ventilate that enclosure to keep it cool. So we ran some tests with a dry, a worst case condition, and we found that the temperature rise was within what the motor would accept. And by throwing more thermocouples into the system, we found out that we were transferring a lot of heat to the oil.
Yeah.
So that's where the heat was going. And we've done more extensive testing since then and found that I think we ran the pumps for like 5 days and found that we didn't overheat the pumps. They were well within the temperature that the motors could withstand.
And if you were with us last week, that's another reason why on a packaged pump skid, it's important for the transfer pumps to have a separate relief valve so that if the pumps are deadheaded, we can bring fresh fuel through that pump head because it not only moves the fuel, but it also uses it for cooling and lubrication as well. The next
All right,
question we have on the chat channel, unless you have one via email, David.
go ahead.
Gene also asked, please clarify what is the priming lift length of pipe from inside of the tank to the pump. So the effective length or vertical is going to be whatever the current level of fuel is in the main tank, that net to the center line of the pumps. So if you have a situation where the tank is almost empty, it could be a lot more difficult than if the tank is full. And in fact, we have one customer here in the Northeast that basically wrote us a little document saying, we understand that if our tank goes below half, these pumps aren't going to work. We promise to keep it full. There's an existing system. They didn't want to replace the very expensive tanks in the ground. So, yeah, depending on the level in the main tank, that can change the dynamics of the system.
You know, I always design for that tank going all the way dry because I just don't think that's a very good answer to say, oh yeah, we've designed the system and it works as long as you keep your tanks at least 50% full. No. I want to be able to use all the oil in that tank. So I'll usually design the system so it can do that one way or another. Um, all right, I had a couple of questions on my email. Get to it. Okay, so how do you determine the exact values to use for ullage and drop tube gap for a bulk storage tank? Ullage is going to be determined by the fire marshal wherever you're at. Here where I'm at in Dallas, the fire marshal wants an alarm to go off when you get to 90% full on a tank, and then they want the overfill prevention valve to shut off flow to the fill line at 95. So in that case, I would use 5% for ullage because you're not going to be able to put more than 95% into the tank.
And is
And
that a
then,
volume value or is that a vertical? Because, like, for instance, if you have a cylindrical tank, right, your top 10% of depth is not necessarily your top 10% of volume.
oh, that's a good point. Yeah, that's vertical. So that 95% is based on vertical. So that 95% height would not be the same as 95% of volume.
So with a round profile tank, you're actually getting a little bit more out of it because your bottom 5 or 10% is a smaller volume, and your top 5 or 10% is a smaller volume.
That's a good point. And then for the drop tube gap, um, you can determine that. And what we like to do is when we do a filtration system or a fuel polisher, we like to put the drop tube for the fuel polisher all the way at the bottom of the tank. And you can either put a T down there so that the oil can kind of get drawn from both sides, or sometimes the contractor will just cut off that pipe at 45, because since water is heavier than oil, if the tank condenses any water, it's going to be at the very bottom of the tank, and we want the polisher to be able to get all that water out of the tank. Your drop tube for your supply pumps should be 6 to 8 inches above that. So again, you got to figure out how much oil is in that bottom 6 or 8 inches. Do a little bit of math to figure out what the volume is, and that'll give you your drop tube gap. But that's the way we like to do it.
Mark Charlin has a question on the chat channel as well. Is suction typically smaller than the discharge? And I think he's referring to pipe sizing. What I'll say is, and in my experience, a lot of times they're about the same size. And the reason that is, even though the suction side is very critical as far as how much pressure we have to work with and preventing cavitation, the size of the pipe itself on the suction side sometimes is less relevant than the size of the valves that are in there. For instance, there are some systems out there that have a 1 inch discharge and a 1 inch suction side, but they're using a 3 inch anti-siphon valve. So some of the larger pressure drop items and systems that you'll see in the field may be upsized without actually upsizing the size of the line itself. And a lot of times the vertical is the largest impact rather than the actual size of the pipe, since for a typical self-priming system, that length of pipe is typically very short.
I got another question here in the email. Do I need a back pressure regulating valve when feeding multiple day tanks? And I think, well, we're talking about the discharge side of the pipe here. The answer to that question is you don't need a back pressure regulating valve in your discharge piping if your header is properly sized. And the rule of thumb that I was taught, and this was actually for natural gas piping, was that the area of your header should be 2.5 times the area of your branch piping. And if you do that, then the pressure drop across your header is negligible, so that you get equal pressure feeding all of your branch lines. So if you've calculated that out and your header is large enough pipe that it's negligible pressure drop from one day tank to the other, all your day tanks should get filled at the same rate if you got into a situation where you're actually filling more than one at one time. So under those circumstances, no, you wouldn't need a back pressure regulating valve. If that piping is undersized and you are taking a significant pressure drop from one branch to the other, then you might use a back pressure regulating valve there to maintain that header at the same pressure all the time. In most cases, I would say go without. And the day tanks are atmospheric tanks, so whatever pressure you fill them at, you're fine. And as long as you're not completely starving the last day tank in the line, I think you're going to be okay without a back pressure regulating valve. And they're a pricey item. It's one more thing. It's a reliable component, but it's just one more thing to go wrong.
And it's pretty rare for a headered system like that for all or most of the inlet valves to be open at once, unless you're first doing a startup. After something's been running for a while, it usually cycles in sequence rather than all together. We had another question in the chat channel here from Mark Drow. In the discharge section, can you give some additional examples of why I would use the secondary pipe option? And I can think of one of them maybe is the one that you just mentioned, David, where you have a headered system and then some supply lines that go to individual generator tanks.
Yeah, although the way that program's going to work is it's going to assume the same flow through all the links. It's pretty easy to see how you would use that on the suction side, because a lot of times it'll be relatively large pipe kind of headering all of your main tanks together, and then the pipe size will drop down on the run to the pump set. On the discharge side, that capability is given to you there anytime you're going to change line size in the discharge piping. And
so for branch flow, you're right, the constant flow rate wouldn't necessarily apply to, unless it was just a single tank calling, which would be worst case scenario, so you could plan for that.
Yeah, and I'm having trouble figuring out in my head why that discharge piping would change sizes, but just in case it does, and the contractor runs the pipe that way, the program gives you the capability.
Okay, I think that covers us for the chat channel. If there's anybody I missed, feel free to pop up and throw your question back in there again.
Okay. I wanted to make a comment on something you said, Alex, for the reason for an anti-siphon valve. So if you get a break in the line in that suction side, and that break is lower than the level of the stored oil in the tank, you have the possibility of siphoning oil out of the tank. And a break in the line is relatively rare, but what's really common is a contractor not tightening up a union.
Or more common than that, because it's accessible to not just contractors, that strainer basket.
Oh yeah. If there's a duplex strainer there and the strainer basket's left open, that can siphon out your entire tank. And
it seems like such a casual thing, that strainer, check it, put it back together, but if you walk away over time, it can be a real single point of failure.
Yeah, that's a good point. And we got called into a site here in a Dallas suburb where they overfilled a day tank and dropped about 3,000 gallons of oil into their parking lot that ran off the parking lot into a pond, and that was over a $300,000 cleanup.
Hmm.
So oil spills are so expensive and such a regulatory nightmare that it's really the worst thing we can do for failure of a fuel system is when we overfill a tank. So that may be why when you talk to us about filling operations, why we're so paranoid about making sure that we have as many belts and suspenders to prevent a tank overfill as possible, because the damage is so expensive.
Absolutely.
So again, we thank everybody for their participation. If you're like me, you've been sitting at home for a month and just dying for more things to do. And that's why we've decided to make these webinars weekly instead of monthly. So please stay tuned. And the next one will be next Thursday. It's going to be Lee Carnahan designing fuel oil systems for the California market. The California market is special because of earthquake codes, and they have an agency called OSHPOD that dictates how you do anything for a hospital in California. And I know that San Francisco and LA have their own requirements, and engineers in California know that everything is special in California. And Lee's been working at least 13 years. I think he's been with Preferred for about 10 years now doing fuel oil handling systems in California. So he is definitely the expert, and I refer to him if I've got any questions about California.
And I'll
So
say, even though some of the things are very different from what we would see here in the Northeast, or maybe from what you would see down in Texas, David, a lot of things kind of migrate across the country. So some of the things that we saw happening exclusively out in California years ago, like boosted fills and things like that, starting to pop up in other parts of the country. So it might give you a little bit of insight on some things that maybe trends in the industry.
yeah, and another example of that is we paid a bunch of money to have our fuel handling systems shake tested so that they could meet OSHPOD requirements and go on the roster in California. And we did it to our standard design. So we ended up taking that OSHPOD California earthquake preparedness language and putting it into our master spec for everybody, because it doesn't hurt and it doesn't cost any more. So why not get a fuel handling system that's earthquake rated, to California standards?
Even though it's a couple weeks out, I think it might be worth teasing even now the emission standards and renewable presentations coming up in a couple weeks.
Right, that's going to be me and Peter Knopf.
I know a lot of people are very familiar with our fuel oil capabilities, but they may not be familiar with our combustion capabilities.
Okay, looking forward to it. And thanks again, everybody, for sticking it through to the end.